Hello everyone, and welcome on the session on serverless with Knative. I'm Moitie. I'm a specialist solution architect at Red Hat. I work with customers within Belgium and Luxembourg, and my main focus is on Kubernetes and Openshift.
Yeah, and I'm Maarten, a specialist solution architect as well, colleague of Dieter, and oriented on the app dev part, being the integration layer as Kafka, 3-scale API gateway, and the development side of Openshift. So yeah, for Knative Openshift Serverless, it was a good mix between infrastructure and app dev. So that's why we're doing the demonstration with the two of us. Yeah, so Dieter,
yeah,
go ahead.
Thanks. So I will give an overview of Knative and its components, and then Maarten will show it in action. So let's start with an overview of Knative. So as I said, my focus is Kubernetes, and Kubernetes is a great platform to deploy all our containerized applications. But still, there is some complexity involved when you want to deploy applications or services on Kubernetes. So just as a simple deployment or a simple service, you would need to create a deployment where you specify the image and the number of replicas. Maybe if you want to do something more advanced and you want to do autoscaling, then you have a horizontal pod autoscaler to be defined. And then in front of that, of course, a service which acts as a load balancer. And all the resources that you create in Kubernetes is in YAML code. So on the right, it's not meant to be read. It's just to show you how much YAML you need to write just for a simple deployment. And then think of updating that one deployment or one service you have to a newer version of it. You can do rolling updates with deployments, but maybe you want to do something more advanced, like an A/B deployment or a blue-green deployment or some testing. And this is harder to do. So what you could do is create another deployment in Kubernetes with another service and then have your own proxy in front of that to steer some traffic to one service and then some other traffic to the other one. And again, all the code you need to write, it's there on the right. And don't worry, I didn't write it myself. I used the famous AI tool to generate that, but it was just to show you how much YAML you would need to write or how much configuration. And this brings us actually to serverless. And most of the people that talk about serverless or introduce serverless, the first thing they say is, well, the name is confusing, or I don't really like the name because there are always servers running somewhere. But the idea is that you don't need to worry about managing those services or the infrastructure in general, which includes to some extent Kubernetes too. So we want to simplify the deployment of your applications, and on top of that, we only want to use the resources that we really need. And this brings us to Knative, because Knative is a Kubernetes native implementation of serverless technology. It's an open source project, part of the Cloud Native Compute Foundation, and currently it's in the incubating phase. And it extends Kubernetes through custom resource definitions, custom resources, to allow the management of your serverless components. So you might think, well, that's even more YAML, and to some extent that's true, but of course we want to simplify things. And there is also a CLI if you just want to avoid any YAML. And there are 3 sub-projects within Knative. So there is Knative Serving, which is about creating these serverless services, make it easy to deploy a service and then do A/B deployments and so on. There is Knative Eventing, which is more about creating event-driven applications. There's Functions, which is to a project, so you can focus on writing functions and how that ends up in a container and is deployed on Kubernetes is abstracted away. While with serving and eventing, you still have to provide a container image. And there used to be another project which was built, but this became so big that it became a project on its own, and that's now the Tecton project. So I will cover Knative Serving and Knative Eventing. Let's start with Knative Eventing. As I said, this is about creating these services on Kubernetes, and there are 4 components or custom resource definitions. One is the service itself, which points to a route and a configuration. The configuration is the desired state, so you define the image you want to deploy, and then every point-in-time snapshot of the configuration is a revision. And then the route is your network endpoint, which points towards the latest revision. So a revision is a point-in-time snapshot of your configuration, and Knative will actually, if you pass a container image together with a tag or even without a tag, then it will translate that for you to an image using the digest. So you really can go back and forth between revisions. Revisions are immutable, so every time that you change that configuration, you just get a new revision. And the route is pointing towards that latest revision by default. But you can change that, so you could do 90% to one version, 10% to another, and then do these A/B deployments and blue-green deployments. Now, revisions can also be tagged, and once you do that, you can actually have a separate network endpoint for a specific revision. So you could create a new revision and then do some testing, and when you're happy with it, change the route to that newer revision. Knative also has autoscaling, which you can also do with Kubernetes with the horizontal pod autoscaler. But the horizontal pod autoscaler scales by default on CPU and memory. So you need at least one running to measure CPU and or memory. But with Knative, you're scaling on HTTP requests entering. And you can also scale to 0. So a request is coming in, it's buffered, a container is started up, it handles a request, and then maybe if there are no requests coming in anymore, you can scale down to 0 again. So you're for services that are not called a lot, you're really lowering the resource consumption. And it also goes a bit faster because with CPU, well, you would have to wait until the CPU is increased before you can spin up newer containers. To configure the scaling, there are a couple of parameters that you can set either on the revision or just as global. So there is a concurrency where you say how many requests can simultaneously be handled by a specific replica. Or there is another option where you say requests per second, where you specify this replica can manage this many requests. So if more requests are coming in, Knative will scale up. As I mentioned, you can use the KN CLI tool to manage your revisions. And just as an example, I've got three codes where the first one is like KN service create to create a service. So you point towards your container and maybe some environment variables. There is, this creates the first revision. If I would do KN service updates, and in this case, I change the environment variables, but it could be a different container image too. Then I get a new revision. So now I have 2 revisions. My route is pointing towards the latest one. And with the third command, KN service update, I'm saying, okay, this revision, 50% of the traffic, and the other revision, the other 50%. And every update is going to create a revision, except when you change the traffic. That's not going to create a revision, of course. So this was Knative serving. The second topic is about Knative eventing. And let's take a step back and talk about event-driven architectures. So with this, we mean that microservices talk to each other through events rather than, or exchange information through events rather than through services like, or through REST calls, for example. So this is in contrast with REST architectures where you would have synchronous communication. Here it's asynchronous. With the REST call, for example, you do a call, and you literally wait for the result. And if it takes longer to get that result, you wait longer. If there is a failure, you would have to build in the logic to to try again or handle that failure. And if you have more consumers of that particular event, you would have to do that call to each consumer. And this is different with event-driven architectures because you create the event and you stop caring about it, actually. So that generates loosely coupled architectures. Your producers don't need to worry about whether the consumer is alive or running or how many consumers there are. And the same thing for the consumers, they don't need to worry about how the event was generated. And they don't need to, they can have different or be written in different programming languages. And you can add or remove consumers and producers all the time. It also makes it more resilient because events can get queued and you can handle event delivery failure, or the broker can do that for you, and so on. The other thing I want to talk about is cloud events. This is, again, another project within the Cloud Native Compute Foundation. And this provides a common schema. So this is to get some interoperability and portability of your applications. So a cloud event has some metadata and your payload, and that metadata consists of some required attributes. There are some optional attributes too, and you can extend it through extension attributes. There are SDKs for different programming languages to use those cloud events, and they're protocol agnostic, but in our case we are using HTTP. So Knative eventing is a set of APIs to route events from consumers to producers. We call the producers sinks in Knative, and we use the cloud event specification for that. And this allows for the creation of serverless components that are driven by events rather than by traffic. There are three concepts I want to talk about. One is called source to sink. The second one is subscriptions and channels. And the third one is brokers and triggers. So Knative sources or source to sink is a very simple concept, right? There is a source, there is a sink, and the source is directly sending events to the sink. But there can be, or there are lots of sources already available, or some sources available. So there is, for example, a ping source that just generates events based on a cron schedule. So you specify some data and to where it needs to go. There is an API server source which looks for API calls in Kubernetes and generates an event on those. And there is a Kafka source, which Maarten will use, which listens to a Kafka topic and then generates events on those. So this allows you actually to integrate with an already existing Kafka in your environment. Channels and subscriptions is the second concept. So in here you would have a channel where multiple sources can generate events and put them or send them to the channel, and the channel or a sink can be subscribed to a channel, and once you are subscribed, you get all the events on that channel. So in this case, you see two sources. So there is source one, source two. They're generating events, and both sinks are getting all those events. So if you only need part of those events, either you need to create dedicated channels or you would need to filter them out yourself. And this is different with brokers and triggers, which is the last one and the most flexible one, I would say, where you would have a broker and sources are sending events towards that broker. And a sink is connected to a broker through a trigger. But in this case, you can have a filter in there. So on the figure, you see there are events of type 1 and type 2, and the top one is getting events of type 2, the lower one of type 1. So this makes it more flexible than channels because of the filtering. So let's say you have type A, B, C, and one source wants the events of A and B, and the other one wants the events of type B and C. In this case, you can just do one broker with two filters or two triggers. if you would want to do this with channels, you either need to have 3 channels, one for A, one for B, and one for C, and then have multiple subscriptions for those, or just one channel, but then the consumer needs to filter out the events that are relevant for that consumer. Again, you can use the Knative CLI to create a broker, create a trigger to connect to that broker. And the later one is also interesting. This is a source binding. You can just send your events to the URL of the broker, but if you do the source binding for a Kubernetes source or a Knative source, you're actually generating some environment variables, so the application immediately knows where to send those events to. So that's the idea of the source binding. By default, there are multiple implementations for channels and for brokers, and some are ephemeral, some are persistent. So by default, there is an in-memory channel for channels. As the name says, it's in memory, so it's not very resilient, but it's good for development use cases or just start quickly. It doesn't consume too many resources. If you want to have something persistent, there are Kafka channel and NATS channel. And by the way, I'm listing here the options that are listed on the Knative docs. There might be more implementations that are not documented. For the brokers, it's the same thing. So there is a channel-based broker, which is the default option. It's backed by the in-memory channel broker, or in-memory channel, sorry. Again, this is ephemeral, good for development use cases. There are other options too. So there is a Knative broker for Apache Kafka, and there is a RabbitMQ broker. Now, as Red Hat, we are also contributing to Apache Kafka. We also productize it. It's called Red Hat AMQ Streams. So the Knative broker for Apache Kafka is what we would recommend and support for production use cases. So I talked about Knative eventing and Knative serving. Knative serving is really about creating these serverless services, create a service and scale dynamically, while eventing is about creating an event-driven architecture. Now, those two sub-projects you can use independently, so you can create a service and then connect directly to a service from, I don't know, the end user or another application, a Kubernetes service maybe, or Kubernetes deployment. And the same with Knative eventing. You can have this event broker that just gets event from a Kubernetes deployment and sends them to another Kubernetes deployment. But you can also combine them together. So a broker would, for example, send events to a Knative service that scales down to 0. Once that event comes in, it scales up, handles that event, and then scales down again. And then you get a combination of an event-driven architecture and an efficient resource consumption. And with that, I will give the word to Maarten.
Maybe first, let's stop the screen extension. Because it will be a bit easier if I can just mirror my screen. No. Okay, didn't think about putting the slides already on the correct place. Okay. And full screen. So what will we demo? Like the presentation already had in the title, we will decompose a monolith into multiple microservices. The monolith itself will be a REST-based application, like you can have for now the legacy Spring Boot micro or mini services, which has person data and address data. And when a person has an address assigned, it becomes an account in the application, and the account data as aggregate is exposed as well. This monolith, the legacy application, we will host on Kubernetes. As we are from Red Hat, it will be on Openshift, which is our enterprise-ready Kubernetes installation. So via the ingress, the pod will be accessible. In the first stage, we will extract the account service, which is the read model of the person and address data combined in the account service microservice. The writes of person and address data are still coming in on the monolith, the legacy application, so we need to bring the databases in sync. For this, we will use decomposition, later more on this one, which sends messages to Kafka, and then the event, the Knative source to sync, will be putting data in the account service. The putting data in the account service will be done via an HTTP request, and like you will see later on as well, it's everything in Knative is then based on HTTP request, but it's not the anti-pattern that's taught about the microservice platforms. Because the HTTP requests are all backed by Kafka backbone in the Knative configurations, so it seems like HTTP, but you still have the Kafka resilience. When we have the account microservice, the first one to extract from the monolith is the address service. The writes are coming in on the address service, but still needs to be pushed to the account service to keep the read model in sync. For this, we will be using the source to sync from Knative. Be aware, this is for demo purposes, like we will have the source to sync, we will have the Knative channel that we're using over here, and we will have the Knative broker and trigger topology. In the end, in the real world, most of the use cases require just the broker and the trigger pattern. But in order to demo it, we will use them all three. And then the last part is extract the person data. So for this, we have then the person microservice with the broker and trigger topology to bring the data in sync on the account service. You see that there's no incoming data anymore on the monolith, and there's no read access anymore on the monolith, so it's then safe to kill the legacy application. With Knative, you can do this in a phased workflow, because in the real world, you don't have the time, and especially not the budget to rewrite applications from scratch. So with decomposition, with Knative, you can put newer microservices next to your legacy applications, phase them out, and for example, the last 20% you can then rewrite if needed, so that you have some phased refactorings. So now, how does this look like in the code? First of all, for the monolith, we have a Kotlin application. If you're not familiar with Kotlin, it's like Java, syntactically a bit different, but it's a JVM language in the Klin architecture setup. So we have an application with a core layer, which contains the domain, the data objects, the POJOs, and the use cases. Klin architecture differs from service-oriented design, that instead of having an address service, you now have multiple use cases that run in isolation. For example, for the creation of an address, retrieving of an address, and the edit of an address. And then same for the person domain objects. We have some infrastructure modules to connect to the database, for example, an in-memory one connecting to Mongo, which will be used in the microservices, and one to connect to Postgres, which will be the one for the legacy application, the monolith. Then the last part is the configuration layer. Mostly in Klin architecture projects, this is just one module, but here we already use it to split the monolith into multiple microservices. And by having this in the same code base, we can reuse the use cases in the infrastructure layer. So only the configuration layer needs to change when we split out the microservices. This doesn't mean if you want to go to Knative that this should be the approach. You can just put a Knative service next to it from scratch. It will be hosted in Openshift. Like here, we have already the first deployment ready, and we already installed the operators to enable Knative, so Openshift Serverless and Kafka. The operators is a concept from Kubernetes to lack some infrastructure knowledge. It's just a few clicks and the default implementation is up and running. Like for example, I don't have too much background in the infrastructure part. I can set up a Kafka in 5 minutes with just a few clicks and the defaults are there. So how do you start with putting an application in Kubernetes? As Dieter already told, it involves some YAML files. So for example, for just a simple service like the uh, monolith, you have the deployment config. I think it's readable. Yep. with the Docker image, the ports you want to expose, the memory you want to allocate, CPU you want to allocate to this, and other metadata. You have a service that needs to be configured. It's the internal DNS of the Kubernetes system that then knows to which deployment the traffic should go. And we expose it via a route. This is already pre-configured, so we have the monolith deployment, service pointing to it, and then the route that makes it external. Let's see if there comes some data out of it. So for the people API, we have a person inside. We should have an address. And I should fix the typo. So there's an address inside. And here in the monolith, just for the demo purposes, we have included GraphQL to expose the account data. We use quercus in order to expose the microservices and the monolith. It's similar to Spring Boot, but made cloud native. It's cloud native Java, which means that you have optimizations for resources, CPU, and you can use GraalVM native images built by quercus. So the GraphQL looks like this, and as well a demo. So we have some address data inside because the address was linked to the person. Now let's start on the decomposing of the monolith. So we hosted it on Kubernetes. Maybe one step back first. You already heard the term decomposition. For the ones that are not familiar with it, it's change data capturing on database level. In the past, for example, the order service, we can map it to the person service we have here. If you would have, or the account service, if you would need to index, create read models out of multiple bounded contexts, like for example, the account data out of person and address data, if it is all contained in the same application, you can put a transaction on it. And if one step in the indexation mapping phase fails, the database changes on your SQL database will roll back. If you now go to distributed systems, like for example, the person microservice, the address microservice, and then the read model, the aggregate as an account microservice, you lose the concept of transactions. What you then can do is put next to your data table an outbox table. First, for example, it will be the person table and the person outbox table. The person outbox table then will contain the reference of the person data object that's changed, created, or deleted, the action, and the timestamp. The Bayesian will then listen on this outbox table, and whenever something changes over there, so in our case, whenever a record is inserted over there, it will consume the data and put it on a Kafka topic. Then you can have a consumer that reads from this topic and brings another system in sync. If now the Bayesian connector would fail, no problem. Whenever it's stable again, it will pick up from the journal files from the SQL database where it left off, so no data loss. On Kafka, your messages are persistent. And if your consumer isn't stable, whenever it becomes stable again, it will start as well consuming the messages where he left off. So you have no chance anymore of data loss. The only thing that can happen is that you have a time window in which the read and write model are out of sync. And why an outbox table and not the Bayesian connected to the data table? It is to avoid security breaches. Let's say, for example, we have the person microservice. Dieter is the owner of the microservice, and I am not allowed to access the data. If for every change we put all the data on the Kafka topics, it can be that other people are reading it and they don't have access to it. So it's better to then just put a reference to this data record in the Kafka topic and let the consumer directly go to the microservice with the authorization still contained in the microservice. So include the Bayesian to extract the account service. We will put the Bayesian, which is a Kafka connector, on the Postgres database that is under the monolith. It will send a message to the Kafka topic, and then we will use Knative source to sync to populate the account data. Let me run a script that will. run some YAML files. So what will happen? We have, first of all, the microservice, the account service, which is exposed as a Knative service. So it will be, at the moment, with 0 instances. And whenever we will have HTTP requests to the service, Knative will start up some instances to process the requests. We have the Postgres connector. Just some metadata so that the Bayesian is able to access the database and will listen on these people changed and address changed outbox tables. It will then put it in separate topics for the tables, but all prefixed with this prefix. So then we have it in Kafka, and then we have the source to sink Knative definitions. Quite easy. You say you have to listen to this topic. And whenever you receive a message over there, you have to transform it, or you just take it and put it on our account microservice on the post via sync path. Similar for the people. Oh, thanks, Dieter. Indeed, I had a typo. And now the Bayesian will be ready. First of all, let's have a look in Openshift. So in Kubernetes, we have the serving of the microservice for the account data. And maybe first create a person object over here, API people. So this is on the monolith. Whenever we create it over here, I expect that it ends up in the account microservice database. So as a body JSON, let's give it a first name. We're at Fox Days. And the person is created. So now if we have a look in the Mongo database that's under okay, let's reconnect. Okay, 1 second. The port forwarding is not done to the Openshift cluster. So with the OC get pod, we have the running pods. We take the one from Postgres.
Yeah, for those that don't know about OC, it's a CLI, but it's compatible with kubectl, right? So you can see it as the same.
And then the same one to connect to the Mongo database from my laptop. Yep, and again a typo. The issue with doing live demos. Okay, and this should be better. Not yet better, so let's have a look. Probably a typo again here. Let's see if we are lucky now, and yes, we are. So the account, so the database for the microservice account is created, and you see already Maarten at Fox is created. So the account service is up and running, and whenever we create person or address data in the monolith via the Bayesian Kafka Knative source to sink, it will be populated in the account service. There is not yet an account for it because the simple logic is telling if there is an address linked to a person, only then it will be exposed as an account. So let's try and populate it with address data as well. So we will extract the address service from the monolith, and we will create a Knative channel in order to bring the account service in sync. Again, let me run some scripts which will do just an OC apply, a Kubernetes apply on resource definitions. Like you saw for the account microservice, the Knative service definition is nothing more than a Docker image and a port on which it is running. A Knative channel definition, which is nothing more than the name. And a subscription, which will then say, hey, from this channel, if you post data on top of this channel, we will push it to the subscriber. So again, the account microservice on the change data, address data via channel paths. In the code, it looks like this. So you have the channel URL. So again, an HTTP post towards the channel. It seems here that you have direct HTTP, REST communication in between your microservices, but Kafka is running behind the scenes, so you will have resiliency built in via Kafka. It's not something that you have to put in the microservices themselves. It's not the anti-pattern that we're applying over here. You will see some specific headers here. It is because the Knative channel and Knative broker trigger topology require to be cloud event compliant. So I run it. Let's see an Openshift if the service is there. We have the microservice address data. I don't need this one. Okay, right mouse click won't work. So let me do it like this. And let's create an address over here. So as well JSON. So at the egg. Brussels. Oh. And still Belgium. You see, now it takes a while, and this is something that you have to keep in mind when you're working with serverless operations. And it should be a post as well. The first request to a Knative service, if it's not yet spun up, it can take a while because you have the provisioning of it. It's a startup time, and for this quercus is ideal because you go from seconds or sometimes minutes in some Spring Boot applications to milliseconds. By default, the quercus application starts in 10 to 20 milliseconds, so you're not speaking of seconds and minutes anymore. Another added value of quercus is that the executable is reduced in size, which means that even the download image is smaller, which results in lower download times, which as well contribute to the startup time of your Knative service. So let's now do it with the correct HTTP method, and an address is created. Let's check in the database, and you already see it over here. The egg Brussels is created. So where are we in the flow? We have extracted the account service from the monolith, which is the read model. We have extracted the address service, and the account service is kept up to date via the Bayesian, still for the person data, and via the Knative channel for the address data. Last part, let's kick out the person data from the monolith and extract the person service. For this, we will then use the Knative broker and trigger topology. So how does this look like? First of all, in the code, you won't see too much difference with the channel definition. And I even named it wrongly. It's a channel URL, but this is the broker URL, to which as well you push a cloud event. In the definitions, it's a bit different. Let me meanwhile run the script to apply them. So you have the person microservice, again, the Docker image with the port. You have the broker, just like the channel, just a name definition. And then the trigger, and here you can do, like Dieter already mentioned, some filtering. So on this broker, if messages are coming in, push it, like we already saw before, to this service on this path. But here we can say the type should be of person changed. Here you can play a bit with, for example, the cloud event types. So let's say, for example, we have financial data, and transactions above a certain amount should be investigated because possibility of fraud. You can say, by standard, by default, go to a service that processes the transactions, and based upon this filter, if a value is there, put it on the second track, which then triggers a fraud detection application, for example. For here, we will use the person changed, and if you saw it in the code, it is the type that we put on the cloud event, so it should work. But yeah, never say never when doing a demo. And then, we have the person microservice over here. Let's now create a person object and directly link the created address over here, and an account should be popping up in the account API as well. So people, already the correct HTTP methods. Let's now say that Dieter is at Fox as well. And let's use the reference for the address that we created over here. Again, some startup time for the Knative service to start. And yes, we have a person object created. So now let's have a look if the account service is giving some data back. So no need anymore to look in the database if everything goes well, because we have a person object with an address linked, so it should pop up over here. And it's popping up. Before going back to the slides, I was mentioning quercus as well. I often get the remark, yeah, it's again something else on top of Spring. But if you then look how it looks like, for example, to expose just some REST endpoints, it just instead of the @rest controller, the @path, @post, @put with the path, and you're free to go. So the annotations are a bit different, but yeah, the threshold, the step to start playing with quercus, it's rather slow. Especially if you're using, for example, Klin architecture setup, it's easy to compare the two. What you can do as well is, for example, your legacy application, keep it in Spring Boot. The newer applications that you put next to it, put them in quercus native, so that you have the advantage of the smaller images and the faster startup times for your Knative services. So back to the slides, we now have the person service extracted as well. No incoming data anymore on the monolith, no read access anymore on the monolith, and the legacy application is gone. No maintenance anymore. So that concludes the demo, and Peter.
Yeah, so as you saw, we were using Openshift, which is our Kubernetes distribution. To run Knative, you just need a Kubernetes deployment, right? You can deploy Knative on top of that. We were using Openshift because it's part of the platform, and we didn't have to do a lot of things to include that. So if you want to play with that, you can create a free developer account on developers.redhat.com. And there is also a developer sandbox. So when you deploy the sandbox, it's basically you get a namespace of an Openshift cluster that we are hosting, and Knative is already enabled. So you can create a developer account, ask for the namespace, and start immediately playing with that. And on the same website, developers.redhat.com, you can also find a couple of labs to play with Knative or with other things too. So with that, thank you very much for being here. See you later.
Yep.